So we've talked generally about the fact that magnetic fields are created by currents. And we've talked kind of about the shapes of those magnetic fields. Now let's get into some of the nitty-gritty and present some equations for how to calculate those magnetic fields. So here we see the equation for the magnetic field due to a long straight wire. So recall that we already learned that the magnetic field forms loops around the wire, and that the magnetic field decreases the farther away from the wire I get, and that we can get a sense of the magnetic field by using right-hand rule number 1. And so in this particular case, imagine I had a current in this wire coming towards you, in which case I would put my thumb in the direction of the current, and my fingers would wrap in the direction of the magnetic field. And so, from your perspective then, we would see this as a counterclockwise rotating magnetic field. Of course, if the current was going this way, then I would turn my right hand around, and we would agree that we had a clockwise rotating field. So this equation here gives us the magnitude of that magnetic field. And so what do we see here? Well, we see that it is proportional to I. Of course, I is the current. And inversely proportional to R. Be careful here. Now, R is not the radius of the wire. We see so many round wires, we see an R, we think radius. Ooh, that's not what that means. In this case, R is the distance from the wire. The distance from the wire. It is not the radius of the wire itself. Okay, and so we see that the larger R is, the farther we get from the wire, the smaller the magnetic field is. Now this guy mu naught, that is the permeability constant. It fills the same role that the epsilon naught filled for electricity. It basically says how well does the magnetic field permeate space around the wire. But really we can just think of it as something that sort of makes the units work out. It's a constant that makes the units work out. Same with the 2 pi. Okay. Magnetic field strengths are measured in Teslas. Nikola Tesla was a famous experimenter in the 1800s. He did a lot of experiments with alternating currents, something we'll talk about in a couple of chapters. It turns out that a Tesla is actually a very large magnetic field. Here are some examples. Of course, you don't need to memorize these numbers. If I'm a few centimeters from a wire with a 1 amp current, see, I'm getting something like microtesla. A 1 amp current would be a moderate household current. The Earth's magnetic field is a little bit larger than that, about 50 microtesla. And this number right here, it does vary depending on exactly where on Earth you are. But if you get any problems in the book or anything like that where it says, how does this compare to the field from the Earth or something like that, we're going to assume this value of 50 microtesla, or 5 times 10 to the negative 5th Tesla for the magnetic field of the Earth. It's a good sort of ballpark average for the Earth's magnetic field. If I'm 1 centimeter away from a 10 amp current, well, now I'm getting up here 2 times 10 to the negative 4th Tesla. A 10 amp current is a sizable household current. Nothing too ridiculous. Moving on. Surface of a sunspot. Surface of the sun. Something like 1 times 10 to the negative 1. So something like 0.1 Tesla. I had some of those out in my last lecture. The neodymium magnets. And an MRI solenoid. So in order for an MRI to function, there needs to be a huge coil of wire, which is a superconducting coil of wire, which creates a huge, massive magnetic field that interacts with the protons in your body in order to create those very, very interesting and useful images. Okay, so just kind of again, a Tesla is a very, very large magnetic field. Here's the shape of the magnetic field, sort of viewed in a slightly different way. Again, here we see the right-hand rule. We see that this shows a wire carrying a current into the page, so like this. And so we see that the field wraps around in a clockwise sense. Okay, so that's another confirmation of the right-hand rule that we learned in a previous lecture. And we see that the field does fall off as I get farther from the wire. Of course, A 1 over r type of shape looks like this. Every time I double the distance away from the wire, I have the magnetic field. It is inversely proportional to the distance from the wire. Let's do a quick example. Compared to the field at point A, the magnetic field at point B is half as strong in the same direction, half as strong in the opposite direction, 1/4 as strong in the same direction, or 1/4 as strong in the opposite direction, or we just can't compare without knowing I. Why don't you pause the recording, give it some thought, and I will see you on the other side. Okay, so here we have the situation. My wire is like this. It is carrying a current upwards. I will use right-hand rule number 1 to see that the magnetic field curls around this wire like this. And so on this side, on the right side of the wire, it is into the board. So over here we have a field that is into the board. And over here we have a field that is out of the board. So we've got some X's over here, and over here we've got some dots to represent a magnetic field coming out of the board. So, opposite direction. We should have concluded opposite direction. Now, let's look at our equation. The magnetic field is mu naught I over 2 pi r. So, notice that if I get twice as far away, I have half the field. So, I think the magnetic field at point B is half as strong and in the opposite direction. PowerPoint degrees. Woo! So these are just vectors, right? And we've been practicing adding vectors and working with vectors a lot last semester and this semester too. So if we have fields from multiple sources, we just add them together like vectors. The same way that we would have added two electric fields together or two forces together. And the real tricky thing here, right, is remembering the direction, right? It's easy to add 2 and 3, but 2 newtons and 3 newtons, well, it depends on the direction. You could get 5, 1, or something in between. So it depends on the direction. And so we need to add these like vectors. And here, we just a sort of conceptual example here, we've got a current carrying wire carrying a current that is out of the page. And then here we have a magnet. And so imagining that we wanted to find the total field here, we see that we have one field due to the current in the wire, and we have another field due to the magnet. And so we need to add this vector to this vector. And in this little picture here, we've illustrated that using the parallelogram rule. Remember, if I draw a line parallel to this vector here, and a line parallel to this vector here, then the diagonal to the parallelogram formed by adding those lines is the resultant, or the vector sum, of the two other vectors. And again, this is the same if we're adding accelerations, or displacements, or forces, or electric fields, or now magnetic fields. Let's try a quick example. The magnetic field at point P is 0. What is the magnitude and direction of the current in the lower wire? Let me get a picture drawn. Okay, so here is my picture, and it tells me that the field at point P is 0. Well, I've got 2 wires here, and so we have 2 sources. And so we could just, in general, we could write the general statement that the field total, and as long as I include a vector, and we don't even have to worry too much about figuring out directions right now, the total field will be the vector sum of the field due to the first wire plus the field due to the second wire. Pretty general statement, and one that I think we can believe in. And the problem statement says that that should be 0. So this equals, well, if I'm going to add 2 things and make them equal to 0, then if they're vectors, they must be in the opposite direction. In order for 2 vectors to add to make 0, they have to be what? Equal and opposite, right? So let's figure out the direction first. Here I'll color this guy green. Put a little green here. Okay, what direction is the field due to the green wire at the location of P? Right-hand rule number 1. Thumb in the direction of the current, fingers curl in the direction of the field. We see that point P, the field due to the green wire at point P, is into the board. That means that the field due to this wire must be out of the board. It has to be out of the board. In order to cancel, it has to be out of the board. Therefore, the current in this wire must be going in this direction, to the left. Okay, so now we know the direction of the current. What is the magnitude? Well, if these two vectors are going to cancel, then they have to be equal and opposite, which means they have to have opposite directions and equal magnitudes. And so what I could write then, I could just take away the vector signs now and talk about magnitudes. That means that the magnitude, and to be explicit, I'll put some absolute value signs there. The magnitude of B1 must be equal to the magnitude of B2. Now I can plug in my equations. We know that the magnetic field due to a wire is mu naught I over 2 pi r. And so now I've just set those two things equal to each other. Notice I've got a mu naught here and here that cancel, a 2 pi here that cancels with this 2 pi, and I can write my conclusion, and we'll jump over here. I can write my conclusion then, that I1 over R1 equals I2 over R2. That means that I2 equals R2 over R1 times I1. So in this case, R1 is 8 centimeters, and R2 is 4 centimeters. So let's plug that in. Okay, the problem statement says that the I1 is 10 amps, and therefore I2 is 5 amps. Well, let's peek at this and see if it makes sense. In order for the vectors to cancel, the field due to wire number 2 had to be in the opposite direction from the field due to wire number 1. Since I'm on the same side of both wires, I'm below both wires, that means that the current had to be in the opposite direction. So we have I1 in this direction and I2 in this direction. Okay? Now, in order for them to cancel, the directions have to be opposite, yes, but the magnitudes have to be equal. That's the only way they can cancel. So I did a little bit of algebra, and you know what? I found out that current number 2 was half as big as current number 1. I wonder if I could have used proportional reasoning to get there. Well, remember that the magnetic field is proportional to I and inversely proportional to R. Therefore, if I am half as far away, in order to get the same field, I need to have half the current. So we could have used proportional thinking and gotten to the answer much quicker, but the algebra works just as well, and we have a lot of confidence in our result since we've done it this way. Another general point to make is that in this particular case, I told you that the magnitude was 0. I told you that the field was 0, and so we ended up here, right? But now, in a more general problem, I might say, hey, you know, here's two sources, what is the total field? In which case, we'd be looking for this right here. So this could show up in a couple of different sort of scenarios. But the setup would be the same. So here's the equation for the magnetic field at the center of a current loop. Notice it's very similar to the equation for a wire. There's just there's no pi down here. Really, that's the difference, right? Now, in this case, R is the radius of the loop. So I keep saying, oh, be careful, R isn't necessarily the radius. Well, in this case, R is the radius. It is the radius of our current loop. And another thing to note is that this is the field at the center of the current loop. Remember, it is stronger near the wire and weaker at the center. And in a more advanced class, we could come up with a formula for it at any point in here. But in this case, we're just giving you a formula for the field at the center. And I, of course, is the current in the loop. And here's this shape. And recall that this shape is very similar to that of a bar magnet, right? And so recall that the north end of this current loop, we could say, is here. The north pole of this current loop would be over here, and over here would be the south pole. So if I just have one loop, I have mu naught I over 2r. Well, what if I have a bunch of loops? Well, I just multiply it by however many loops I do have. So in this case, I have a loop of wire. And how many turns are in it? Well, let's see. It looks to me like we have 1, 2, 3, 4. So if I was trying to calculate the magnetic field at the center of this loop, then I would use n equals 4, because I have 4 complete turns of wire. And again, that is the field at the center. So in a way, we don't even need this equation, because we would just plug in n equals 1 to this equation. But this is the simpler version, so we start here. If you've got n of those, we multiply the field by n. So the fields just add. Now, if I have all of these coils smashed together, then we call that a coil or a loop of wire. However, if I stretch it out a little bit, I would call it a solenoid. Again, in this model, to be precise with our language, a solenoid has some length, a loop does not. Interestingly, notice that R does not show up in the solenoid equation. So we actually don't care how big the solenoid is in this direction, right? We only care about how many turns. And not only that, notice that it's not just the number of turns that show up. It is always n over L. So it's the ratio of how many turns per length. So here, this solenoid has a low n over L, and now it just got a little bit higher. So I would expect this to have a higher magnetic field in the center than this, simply because it's got a larger n over L. Here is a nice picture of what the field due to a solenoid might look like. We can use right-hand rule number 1, alternative version, to confirm that if the current in the solenoid is coming out of the page on top and into the page on the bottom, then the field on the inside is going to the right. Recall that for an ideal solenoid, the field outside of the solenoid is 0. And so we will assume that we only deal with ideal solenoids in this class.